on in. Well, I'm excited you're all here. Thanks for coming right after lunch. Hope you had a chance to digest your food. What we're going to talk about today is why I think we are all of us. This group of people in this room at this conference, we are on the edge of one of the most significant technological advances of the 21st century. Now, I know we're at a Tableau conference, but I'm not talking about Tableau 10.0 or 10.1. I'm not talking about even really any software technology. I'm not talking about the next revolution in business intelligence. What I am talking about is how we are the people who are just beginning to exploit the science of how and why our brains see and understand data the way we do. So I'm Jeff Pettyross. I work at Tableau. I lead our user experience design team in our engineering group. So I work with some of the people you saw this morning, like Francois. Dev's on stage this afternoon. Is a few more of my colleagues. I'm much louder all of a sudden. And in addition to those folks, I get to work with people on our research science team who are at doing some of the most cutting-edge research in computer science today. Like some of the NLP, the natural language processing you saw. I work with Vidya Settler, who works on that technology, developing that. But one person in particular I want to call out is my manager, our Vice President of Research and Design, Jock McKinley. So Dr. McKinley, 30 years ago, he was at Xerox PARC, the Palo Alto Research Center. You may have heard of it. That's the place where they invented the graphical user interface and the mouse. Well, right about the same time that Stu Card was doing some of that research, Jock was there. And he was on the team that coined the phrase computerized information visualization. So I'm lucky enough to work with one of the people who actually invented the field of taking data and starting to look at it on computer screens in a graphical way. And today I'm going to share some of what his research has uncovered and some of what he's shared with me and where we're going to be going in the next decade. So I said Jock was doing that research 30 years ago, but we've been doing database a lot longer than 30 years, right? Actually hundreds, thousands of years in some cases. So I'd like to take a look at this example. Some of you may know it already. This was done by Charles Minard in 1869. It's about the end of the French Empire. But let me set a little context before we go into this. So in 1801, France looked a lot like it does today. In 1804, Napoleon became the emperor of the French. And he started a decade-long campaign of military expansion. He conscripted the young men of fighting age, built his Grande Armée, and basically ended up doing this with the French Empire. So in 1812, Napoleon is at the height of his power. He wants to secure a trade deal with the British at this point. In order to do this, he's going to go show off his military prowess by defeating the Russians. So he gathers his army in the northeast corner of the empire in Poland and heads off toward Moscow. This turned out to be one of his biggest mistakes and the reason why France looks like this today. So this whole story, the beginning of the end of the French Empire, is captured on one sheet of paper here. So let's walk through it together. The fat orange line represents the march of the Grand Army from Poland to Moscow. And it marches from the left to the right. You can see as it goes, it gets a little bit thinner and thinner because the thickness of that line represents the strength of the army. So the whole trip across Russia, the Russians were attacking. They'd come in guerrilla strikes. They would kill some of the French soldiers. They would burn all the crops, depriving the French of a supply line, and then the Russians would retreat. Well, the French were trying to get to Moscow. They didn't have time to go chase the Russians down. And time after time, the Russians mounted their offensive, killed a bunch of the young Frenchmen, retreated, burnt the crops. So by the time Napoleon's army got to Moscow, many of them had already been killed. But Napoleon was still determined to score his victory at this point. Unfortunately, here's where the Russians released their masterstroke. By some accounts, Moscow was 3/4 in flames when they arrived. There was no government there. The Tsar had left the city. There was no one to defeat. Now, Napoleon, as I mentioned, was a military dictator. If you don't have someone to beat, you can't win in that condition. So now, it's September in 1812. It's starting to get cold. Has anyone ever been in Russia in September? It's not the warmest place. So the French army turned back around and started heading back toward Poland. And now they had two things going on. The Russians continued to attack, continued to strike, continued to burn the crops, and the temperature is getting colder, and you can see that in the line graph that runs across the bottom. That one actually reads from right to left because it follows geography instead of time. Until finally at Maladzechna, you may not be able to read it from there, but it's 47 degrees below zero. I don't remember if it's Fahrenheit or Celsius, but they're very close at 47 below. So the French army was literally decimated. Napoleon never secured his victory. His allies turned on him one by one. He never got the trade deal with the British, and it was the end of the French Empire. This whole story of hubris, of staggering loss of life, of defeat, of skillful tactics, is all captured in this one sheet of paper. Now, when Menard drew this, he had his own political reasons for drawing the picture this way. But I maintain the reason why we still look at this, the reason why Edward Tufte spent so much time discussing this viz in one of his books, is that Menard had this intuitive sense about how to tell a story with data. He knew how to use things like color and shape and size to start telling a story in a way that drew us all in. But what's happened in the last 30 years is we've begun to understand the science behind why. We've begun to unlock the cognitive and perceptual principles that inform why data viz works. And that's why I call this talk the beautiful science of data visualization. Together we're going to explore some of these principles and learn how we can apply them to our work and help usher in this revolution. So, we all have brains. Scientists have studied them. And there are many different parts to our brains. It's not just a pile of goo in our heads. So for example, up here in the front of your head, you have your prefrontal cortex. It's responsible for things like personality and decision-making and higher reasoning. And then in the back of your head, you have your visual cortex right here. I shaved just for this talk. So the visual cortex is like an information superhighway. It takes data from the outside world and moves it into our brains faster than we can think about it, faster than we can actually cognitively process it. So it actually helps us change how we think. So let's go on a little tour of the brains together before we get further into that. And we're going to explore different parts of our brains together. So first, a little exercise to wake up after lunch. How many dots do you see? This isn't the hard part, I promise. 9. So why 9? Well, it turns out that our brains have one part of them that knows how to count up to 5. It's called numerosity. We can instantly count numbers up to 5. And there's a different part of our brain that's responsible for counting large numbers, estimating, oh, it's a lot, it's thousands or millions. But to get to 9, we use something called numerosity. We use counting. And so you get to 5 quickly, and then you count 6, 7, 8, 9. The counting center of your brain's lit up if you played along. So now we've got the counting center warmed up, count some more. How many 9s do you see? Well, maybe this will help. I promise, I colored them all. How many 9s do you see now? I get 12. So what just happened? How was it that this was so hard to see all the 9s, but this, they pop right out? Well, that's the power of the visual cortex in one respect. Visual pop-out, perceptual pop-out, is something that accountants use. Right? They write negative numbers in red because you want to see them in distinct contrast from the rest of the information. So now what we have is our counting centers going up to 12, and we have our visual cortices noticing the red against the gray background, and the two parts of our brain start coordinating. Now, I grew up in the US, and as a product of this educational system, I never learned how to count red 9s. maybe you did wherever you grew up. But our brains can intuitively connect different parts and make them work together like this. So let's start using more parts of our brains together. This is some real data. Each number here represents a country, specifically a country in the Americas or Europe, and each number represents the percent of that country's economy that they spend on the military. So, for example, this 5 here is the 5% that the US spends on average on the military year to year. So, if I wanted to know how many countries in Europe and the Americas spend 5% or more on the military, well, you could go through and try to find every number 5 or larger, or we could color them, and you can see quickly there are 3. Now, we can also do something else. We can start looking at the data positionally. And so now we sort it, and the small numbers on one side and the large numbers are on the other. This adds a new layer of meaning, a different part of our brain lit up to inform us about what we're seeing. So now if we add another region, say the Middle East, new information jumps out. We see all those yellow numbers. We make meaning of it, but first we saw that splash of yellow. And then we went back and brought in our cognition and said, oh, those are all countries, and those yellow ones are all bigger than 5. And so together our visual cortex and our cognition go back and forth, interpreting the data. Now, we've used position so far to look at size, so smaller to bigger, but you could also use position in other ways, like geography. So now we've taken this information and displayed it on a map. We still get the fast visual grouping, so we can see how the countries come together, how all those countries in the Middle East are spending more in the military. You might also notice the 2 European countries are gone from this map. They're 2 of the smallest ones, so they just don't show up at this scale. So we're having this dialogue with the data almost, right? We ask a question, what countries spend this much? And we answer it one way, and then we get new information, and we answer it a different way. Now we can add yet another layer of data. What if we used size to tell us something about absolute spending? So now each circle tells us the amount of dollars they spend on the military. And you can see countries like England and France and Germany spend more on the military than their Middle Eastern counterparts, but it's just a smaller proportion of their economy. So one part after another, we went on a little tour of our brains together. We lit something up, we lit up another part, and these parts of our minds all coordinated together. And we did it quickly. We formed meaning, understanding rapidly, looking at each picture. But there's a downside to all this power to rapidly form conclusions as well. So I'd like to tell a story from my childhood. So I remember when ATMs were invented, cash machines. At the time, my mother worked at a bank, Connecticut Bank and Trust. So it's in the northeast of the US. And Connecticut Bank and Trust was one of the first banks to introduce cash machines in that part of the country. And they knew they had a problem. There's a trust problem. Like now we know cash machines work, but at the time, the way I got cash is I would go up to a person and I would say, may I please have $100 from my account? And if they gave me 5 $20 bills, we were good. And if they didn't, I could just point it out. But if I went to a cash machine at 11 o'clock at night and they gave me 4 20s, what would I do? Who would even believe me if I went back the next day and said, you didn't give me enough money? So there was a trust issue. So CBT, Connecticut Bank and Trust, solved this by literally putting a friendly face on their ATMs. Meet Barney. So Barney was the logo of the CBT cash machines. It's a pretty good piece of design, I think. It's just 3 circles, a line, a couple triangles, a couple curves, and we all see a face. And not just a face, but one that suggests a sense of trust. So I'm going to put Barney away for a minute and tell a little bit about how successful this was. So Barney was so successful that, first of all, you could go to any bank, or people would talk about cash machines at any bank, and they would say things like, I'm going to the Barney machine, even if it wasn't a Barney branded machine. This is like a marketing person's dream, right? And then they also did research. They wanted to find out why was Barney so successful. So they asked people, what do you like so much about Barney? What do you think people said they liked the most about Barney? Well, Well, they said his smile, which was really interesting because he doesn't have one. And also, it's just a bunch of lines. So what's going on here? Well, I think what happened was our brains too rapidly drew conclusions. We get this idea of face I trust, and we stick it too close in our heads to something like smiling. So trying to access our knowledge and make sense of it can be sort of like trying to make sense of an Escher drawing sometimes. Just like in this drawing, you get walking and stairs and up and down next to each other. In our minds, we get trust and smile mixed up also. Now, it's important that we can rapidly draw conclusions too, to be clear. Imagine how hard it would be to drive if every time I drove down the road, I was like, there's a yellow line. What do yellow lines do? Oh, there's a red octagon. What am I supposed to do with that? So we need to be able to rapidly draw conclusions to be able to move through society. But we also need to be aware of the conclusions we draw rapidly and incorrectly. These are called cognitive biases. There are dozens or hundreds, depending on how you want to count them. Some examples: stereotypes. All software engineers are introverted. That's a good stereotype. How do you know you're dealing with an extroverted software engineer? They look at your shoes when they talk. I'll be here all week. But also there are other ones, like primacy and recency are two more examples of cognitive biases. So if we see a list of things that are unrelated, we tend to remember the first things and the last ones. Our brains just do that better. Think of the last time you watched the credits on a TV show. The biggest stars were at the beginning, and the special guest stars are at the end of the list, because their agents know to negotiate for those spots because those are the ones that people remember. That's how they build their brand recognition. So cognitive biases work for us and against us. But what does it have to do with visual analytics? Well, this gets back to that superhighway thing I was talking about. Our visual system is enormously powerful, so when we apply it, we get to strip away all the false information, or at least get new information to help us inform our thinking. So how does this work? How do we sort of hack our brains, if you will, to get new information into them when we've been trained so well to form conclusions based on what we know? We're very smart people, and we're very proud of how intelligent we are. So science, this research we've been doing in the last 30 years, has begun to teach us how we can start displaying information to create meaning visually. And here are some ways we've learned. We saw some of this already today, right? Length and width. We saw color when we tried to pick out those nines. But rather than just give you a list of visual properties, I'd like to give you a demonstration of how rapidly this actually works in the brain. So to give you a demonstration of how fast this works, I'm going to show you a video. This was done at North Carolina State University by Professor Chris Healy. And what he did was, he's going to give us another little test. I'm sorry, the tests will end soon, I promise. Unless, of course, I didn't leave the test on my computer. All right. So what we're going to do is watch this video together, and in it, we're going to see a series of images, and each image is going to be a short test. So first, the test is, do you see a red circle in a field of blue circles or not? So yes, it's here. And no, it's not here. It's there, but not there. Now the images are going to go faster and faster. And as they do, you'll notice this is actually pretty trivial, right? We can rapidly pick out whether that red circle is there or not. That's just an example of how fast our visual cortex informs our cognition, our understanding. Now here's another example. You need to see if there's a red circle among a field of red squares. So it's there in that one, and it's missing from that one. Now these are also going to start going faster and faster. And my experience of watching this video is I know whether the circle is there before I actually know it's there, if you take my meaning. Now, it turns out we can't just mix these visual features randomly. So now try to find a red circle with blue circles and red squares. It's not there. It is there. It gets a lot harder all of a sudden. So we can't just mix any two visual features, but at the same time, we don't need to spend years researching how we see to understand this, because we can rapidly look at this and make sense. What is no longer jumping out at us? There are a couple other features I'll show briefly, and then we'll move on. But color boundary is another one. We're very good at seeing how a group of color ends. So here is the line horizontal or vertical between the red and the blue. And you notice we can start mixing shapes, and we can still see this boundary. This is closely related to clustering, right? If you look at a scatter plot and you can see some marks together that might share a color, that pattern jumps right out at us when we're interpreting that data. Now, the same thing happens with the shape boundary as well. So we can see boundaries between circles and squares. So that one was vertical, and then this one is horizontal. And we can have mixed colors, and we still pick out these boundaries. So our visual cortex evolved over time to help us see and understand data in entirely new ways. But it wasn't about data back then. It was probably about being able to spot the cheetah waiting in the grass. So let's apply this a little bit. How do we actually use this information? I'm going to go back to data 101 for a moment. There are three kinds of data, right? First, there's categorical data. This is things like continents and people, stuff you can put into concrete groups. And you have ordinal data. These are groups that go in a certain way. And we have a strong sense of how this ordering goes, right? If I had a traffic light that went red, green, yellow, it would feel out of place. And then quantitative. This is data you can do math on. You can compare them, you can subtract them. You can get a proportion of them, for example. And you'll notice that dates are both ordinal and quantitative. They're things you can bucket together, everything from January, or you can say, well, I want to know things that were within 15 days of this transaction, for example. So what are the best ways to communicate these different kinds of data? What have we learned about how we see information to help us explain this? So if I want to explain categorical information, the strongest way to do it is with position. What does that even mean? It's really, really simple. Take a bar graph. There are 5 bars. They're in a different position. I know those are 5 different categories. It's really that simple. But things like color hues too. So all my blues are one thing and oranges are another. We've all seen that millions of times in Tableau. Shape and clusters are all different ways of showing off categories of data. Now for ordinal data, for ordered data, position is also really relevant. Going back to the stoplight example, think of how badly the cognitive dissonance fires in our brains if traffic light was in the wrong positions in the light. Now size is another way to communicate, small, medium, large, and so forth. Color hues. There's a spectrum along which colors like to travel for ordinal data in our brains. And then finally, for quantitative data, position is still the strongest encoding. So how far along the axis does something show up? And length and size. Finally, I want to point out orientation at the bottom, change. This is part of why line graphs are so effective for telling us whether something's increasing or decreasing. Our brains see vertical and horizontal and increasing and decreasing rapidly before we start trying to make sense of them with our cognition. So I want to go back now. I hypothesized earlier that the reason why this viz has stayed so popular over time is because it's such a powerful way of telling a story. So looking at the science, or looking at it through the lens of the science we've gotten in the last 30 years, we can see, what did he do? He used color hue to indicate a category, the direction of travel. Size communicates troop strength. Orientation indicates both direction of travel as well as the plummeting temperature. Position indicates the temperature itself and how low it's going. So 150 years ago, Menard intuitively started applying these principles without understanding how they worked. Let's take a look at some other sort of time-tested examples of data viz. You may have seen some of these. I think I got pins with them on it last year. This is from London in the 1800s. Dr. John Snow discovered that cholera was transmitted in water. Until he reached this conclusion, everyone thought it was just a miasma of some kind in the air. So he did research, reached this conclusion, and used this map to tell people about it. So this pump here on Broad Street was infected with cholera. Each of these black lines represents one person who died of cholera. And you can clearly see how those deaths cluster around that well in the middle. So what did he do? Well, he applied principles of data viz without knowing it. Positional information is used to indicate geography, like it is in all maps. The length of the black marks, because I think those black marks all kind of coalesce together, indicate something about the number of deaths. Clustering shows us how they're all centered around that one spot. Again, applying these principles of visualization. Florence Nightingale did this one. This is something else from England in the 1800s. She wanted to convince Parliament they should spend money to prevent disease because it was killing their soldiers in the Crimean War. So there are three colors she uses here. She uses color to indicate how the soldiers were dying. The pinkish area are deaths actually dying in the battlefield. The much larger bluish-gray fields were preventable diseases. She was able to use this to get them to spend money in a way that words and numbers were never able to do. And what did she do? She used position around the circle to indicate an ordinal value, the months. Size indicates the quantity of deaths. And again, color hue is related to the cause of deaths. As a side note, she was the first woman inducted into the Royal Statistical Society and also was later honorarily inducted into the American Peer Institution. So one last example. This one is from over 1,300 years ago. The Dunhuang star maps are the oldest known complete preserved star atlas. What do they do? Why is this still around now after all this time? Well, I think it's because they use good data viz. They use position to indicate the position of the stars, but they also use lines to connect those shapes, clustering to tell us about the constellations they saw in the sky. And they use color hue to indicate a category. There were 3 different schools of astronomy in China at the time. Each of those 3 schools is represented by orange and black and white. So for over 1,000 years, we've been starting to intuitively apply the principles of data visualization, cognitive and perceptual psychology that we didn't have the science behind yet. So let's take a look at this ancient fascination we have with stars and look at it today, too. So let's take a look at Tableau. What I've got here is something about the Kepler Space Telescope. You may have heard of this. First of all, I've got to nerd out for a moment and just say that again. This is a telescope in space. So the Kepler Space Telescope, it's great because once you get a telescope up beyond the atmosphere, you get past the heat pollution and the light pollution and the pollution and the clouds, and you get a much clearer image of the sky. And what the Kepler Space Telescope does is it stares at one spot in the sky for a very long time and just notices if certain stars get a little bit dimmer, and then do they get dimmer periodically? Does it repeat in a certain pattern? Because if that happens, there's probably a planet passing in front of that star. So the Kepler Space Telescope is one of the primary instruments we've used to start detecting exoplanets, those other places where planets are. So I've got the data here, and let's start by seeing how many observations has Kepler made to begin with. So I'm going to pick up Kepler Object ID and drop it on detail. And when I do, we're going to see one mark for each of the planets it thinks it's found, if you'll let me personify it for a moment. So we rapidly understand something about this data. It's not dozens, it's not millions. Turns out it's a few thousand, about 8,000 different things it thinks might have been planets circling stars. But how many of them are actually real planets? Well, scientists call that disposition, astronomers in this case. So I'm going to pick up disposition and drop it on color. And now our sense of proportion and clustering comes into play. And we see about 1/5 of them are orange, which means We bring our cognition and read confirmed. So a fifth of them are actually planets orbiting stars. We have other data to correlate that and confirm it. The big blue band in the middle is the 40% or so that are unknown. And then the gray ones, we've confirmed that was just noise in the data. So we got a sense of the size of the data and the proportion, but how are these stars arranged in the sky relative to each other? Well, here on Earth, we've got latitude and longitude. Up in space, we've got declination and right ascension, which are the same thing. So I'm going to start spreading our data out positionally. I'm going to take right ascension and put it on columns and declination on rows. And just like a map, I don't really care whether I include 0, 0 on this scatter plot. And when I do that, we're going to see this data has a certain shape. And when I saw this for the first time, I got kind of curious. Where did this come from? I know when I look up in the sky, the stars don't look like that. So I did some research of my own, meaning I used Google. And this is what I found. That's what the inside of the Kepler Space Telescope looked like before they launched it. So each of those blue squares is a CCD, a charge coupling device, the same thing you have inside your phones. So that is what's used to take the pictures. And you can see how big they are, and imagine the resolution that this thing takes pictures at. Just a little bit of trivia, the little tiny blue squares in the corners, there's 4 around the edges, are what they use to align it. They take a low-res image first, make sure it's still pointed at the right spot, and then they take the expensive, bigger images. So we'll go back to the data again. So we know how the stars are in relationship to each other. We've learned something about the instrument that's used to collect this data. Now, how much of the sky has Kepler actually looked at? Well, I mentioned that right ascension and declination are something like latitude and longitude. So I'm going to spread right ascension out from 0 to 360. It wraps all the way around the globe. And then declination goes from negative 90 degrees to positive 90 degrees. And now we can see this little postage stamp of the sky that Kepler's been staring at for a few years now. So we can build a spaceship. We know roughly where to aim it. We can do a little course correction on the way. But which star do we want to go toward? Well, it turns out when you're looking for a planet to live on, you don't want it to be too hot, and you don't want it to be too cold. You don't want it to be too big, and you don't want it to be too small. So they call those Goldilocks planets, because they're just nice and comfortable. So as a proxy for this information, what I've got here is this data about the planets out there, the exoplanets that Kepler has discovered. I've taken out the false positives in this data. And I've got the radius going vertically. So this is a proxy for or it is actually the size of the planets. Bigger at the top, smaller at the bottom. And then I've got the orbit size running across the horizontal axis, the x-axis, as a proxy for what's the temperature, because the closer a planet is to its star, the hotter it's going to be. So I did some more research. I Googled further and discovered that the equilibrium temperature range at which humans start getting a little bit too uncomfortable is above 275 Kelvin. So let's get rid of all those planets. And then we can live in a planet that's probably about 1 3/4 the size of Earth. Much bigger than that, it either turns into a gas giant or the gravity is just uncomfortably high. So with a couple quick filters and a scatter plot, we're left with 9 planets out of all the candidates that Kepler's discovered. So the astronomers who look at this data, they want to find out where are the actual possible habitable planets, because maybe someday we might go there, or we want to listen to them for extraterrestrial life, or whatever we want to do with this information. And they've discovered that there are actually 8 exoplanets that are Earth-like enough they could probably, or they might be able to sustain human life, even conceivably. And I've got that set here, and I'm going to pick it up and I'm going to drop it on shape, and when I let go, what's going to happen is the 8 planets they found are going to still be colored in, and anything else is going to be left as a hollow circle. So with this really fast, easy analysis, is there anyone who's actually an astronomer in the room? Curious? Okay. I have had astronomers in the room, and they've now fact-checked this talk to the point where I'm feeling pretty good about this. Including actually the spouse of the person who named the Goldilocks planet, so that was very interesting. But anyway, Quick and dirty analysis. None of us are astronomers. None of us are even scientists in that field. But we're able to take this data and use our visual understanding to get a sense of how it's shaped. We're able to use color. Go back to our talk. So we're able to use boundary detection to notice things like the shape of the instrument. We're able to use clustering to see something about how many stars there were and where they were in the sky. We use color to understand what they were like, how hot they were, as well as whether they were actually real planets out there or not. We went back and forth between asking questions about that data that were very cognitive questions to answering them in this intuitive way where we get a flash of intuition from our visual cortex, and then we would understand it cognitively. And we went back and forth between cognition and visual processing over and over again, asking and answering these questions. It's what we do every day when we use Tableau, when we look at data visually. Now, what makes this science, this whole idea, so ridiculously cool to me, what gets me so excited about coming to work every day, is that data visualization is opening the funnel for how much information we can process as human beings. We have more and more data all the time, and our ability to understand it is at the fringes of what we can do. And we're the people bringing the technology to fruition that can actually help us do that as a people. Now, of course, this isn't a one-time activity either. Data is always coming in. New information comes to light. Something new happens, and we go through this process over and over again of seeing and understanding data. We start with a question we want, this task. And then we follow it around. We get some data, we choose a visual mapping, we view it, and so forth around the circle. I hate reading slides. But this is what we call at Tableau the cycle of visual analysis, this process we go through over and over again of asking and answering questions. And of course, it's important that as we look at data, we have tools that support us in being able to ask and answer the questions in fluid ways. Because we get data, I mean, this circle is perfect, right? You get your data, it's exactly the right data. And you choose a visual mapping, and it's a perfect one, and you reach a conclusion, and you go share it with the world, and you just go do it again. But of course, that's not really what happens, right? We get the data, and I was expecting 5 million rows, and I got 5,000. Or I thought there were going to be 30 categories, but there were 3. Or I view the data, and it has exactly the wrong conclusion from what I wanted, so now I have to go figure out why. And so that's why we have all those arrows in the middle, too, because you need a support system as these visual processing tools that our bodies are. We need a support system that lets us ask and answer these questions fluidly. And so in the software, as we design it, we apply this idea of a fluid conversation. So when we look at Tableau, we go back to those principles of visual analytics. Remember, position is the best way to understand data of any kind. That's why we put the rows and column shelves right there at that heroic location at the top of the screen. It's the most important way to understand data. And you can take it to look at categories or at ordinal data or at numbers. And the other important encodings, color, shape, size, they're all one drag and drop away. There's a reason why those are the things you can do fastest and easiest in Tableau. It's because it's the way our visual cortex processes information the most powerfully. And then beyond that, there are best practices and things like show me. I have all this pile of data. I want to look at these pieces of it. Give me a pointer in the direction to go. So this is just 2 examples, the shelves and what's there, and show me of how we apply these principles of perception and bring them to our user experience design. So there are 4 principles I want to talk about how we want to think about data. And this is certainly what we've done at Tableau, but I think as all of us wander through our data journeys, even before I started working at Tableau 5 years ago, these are patterns in how I noticed it was effective to use data. First is that our conversations with data are incremental. We build our understanding over time. We ask a question, we answer it. We ask another question, we answer it. Sometimes the best viz is a really simple one because it tells the story immediately to the whole room. You don't have to spend time trying to process it. The second thing is we want data to be expressive. Think of all the different kinds of information there are in the world and how horrible it would be if we couldn't express them in a rich way. So whether you're looking at music that's been released and whether it was more popular in the US or the UK, in that viz in the top right, or looking at which animal species or which mammals in Africa are declining or increasing in population, or something as mundane as lamb production in Belarus. Molchania yanyat is what that viz is called. You may notice that the blue line representing lamb production goes way down to 0, and Molchania yanyat means silence of the lambs. But that humor, right? That little moment of, I'm telling a story more interesting here. There's something to this. We want to be expressive with data. We also want to be able to talk directly to the data itself. Right? We don't want to have to get a proxy to it. This is why we're investing in things like Hyper, so we can get data in more quickly, even at giant scale. But from spreadsheets up to large databases, whether they're on-premise or in the cloud, you want to be able to get to the data wherever it is, because if it's somewhere you can't get to it, it's meaningless. We can't make sense of it. And then finally, data exploration wants to be direct. You want to be able to point to something and say, tell me what that means. So whether it's a tooltip or it's a filter or it's a highlight, however you're actually reaching out and touching the data, that's an important part of that conversation, because you don't always want to have to do a new query. Sometimes you just want more information about what you already see. So I'm going to wrap up soon. But before I do that, I wanted to tell a little bit more one more story about the history that got us here. So humanity as a species, we've been using tools long before we understood how they worked. We had the wheel and we had fire for a long time before we understood the physics or chemistry behind them. So I want to step back in time before we had things like pre-attentive attributes and understood what they were, and cognitive psychology and labs in Palo Alto called Xerox PARC. So over 500 years ago, explorers from Europe discovered the Marshall Islands. Now, no doubt that this collection of white men was very smart and brave to actually get in ships and sail off into the middle of nowhere. Nonetheless, the people who lived on the Marshall Islands were surprised to find out they needed to be discovered. So the Europeans showed up in these giant ships, right? Sails, sextants, maps, compasses. They had all these tools that helped them explore the world. And they show up in the Marshall Islands. Now, when you stand on the shore of one of the Marshall Islands, you might see something like this. They are miles apart. You can't see them from each other. But then the Europeans saw something amazing. The Marshallese would get into their canoes by day, so there were no stars out, and they would paddle from island to island without getting lost. Now, it turns out what was happening is as the Marshallese got in their canoes, they could actually feel the shape of the water moving around them, where the currents were, how they were reflecting off the undersea shores of the other islands. And by a sense of dead reckoning, they knew where they were at all times. Digging into it a little bit more, you might not be surprised to find out the way they did this was using data visualization. So this is over 500 years ago. So these navigators, in part, I'm sure also had good technique, but they used data. So this is a sample data set, I kid you not, or an example of a sample data set from the Marshall Islands. This is the coffee chain of the Marshall Islands, if you will, the superstore. So navigators, experienced navigators, would use super simple data sets like this to teach new navigators how to build their own maps. So this curve here represents a current coming from the right. And these other 4 curves represent 4 more currents. They would use rocks or shells to indicate where the islands actually were. And so with this system of visual understanding in mind, they would build maps of how to get from island to island. Like I said, this is just sample data. This is what a complete stick map might look like. Now, as a side note, it's interesting to me that they didn't actually share these with each other. Everyone would build their own stick maps. But I can imagine that they were standing on the shore of one island and someone walked up to the other one and said, "Wow, what's that thing?" I said, "Oh, it's a stick map. I can show you how to use it." And that was when Land and Expand began. But now today, where we are, we don't just have charts and graphs. Right? We don't just have fire and the wheel. We now have the equivalent of things like exothermic chemical reactions and angular momentum. Now we understand how our brains actually see and process information. We know something about cognition and perception and how the parts of our brains work together. So just like before we had physics and chemistry, we were making progress, but then suddenly we unlocked the Industrial Revolution. We invented cars and trains. When we mastered electricity, we started getting computers and telephones. Society was literally revolutionized by the science we understood. So now we are the providers, the purveyors, the people who understand the science that is beginning to power the 21st century. We know why we can actually see and understand data. So even though some early pioneers began doing visualizations hundreds of years ago, we now know why they work. We have the potential to change the shape of this planet and how we move through it as people. And that's why I'm so excited to share this with you. So thanks for your time. So I can take a few questions, or we can recover from lunch elsewhere. It's up to you. Any questions? Yeah. What was the beginning of the question?
Is there truly a rank of better
Yes.
one or the other?
So, well, the question is there a better visualization of one over another depending on what kind of data you want to show? Am I saying it correctly? Yes. Now, I wish I could offer you some like metric, like, take your cell phone, take a picture of it, and yes, that's a better viz. That doesn't exist, but definitely for sure. So when you're looking at the data, or when I'm looking at data, what I try to think about is what is the most important part of this that I'm trying to convey, and go back to the list of ways of doing it. So position is at the top of the list for a reason, because that's usually the most important way to do it. It's often why we start doing visualizations with a bar chart, because I want to take my categories and understand them first. So I take some position, I take two positions actually, one categorical and one numeric, and then I look at them that way. So absolutely, there is a better and worse way. That being said, there's also a lot of art to it as well. Right? We're trying to tell compelling stories. If you think about all the data in the world and how we choose what parts to use to tell stories with, there's certainly a bit of an ethical constraint, but there's also one of creativity. How do I pick elements that I want to be able to do and tell a story with them in a way that draws in the viewer, whether it's something as prosaic as an annual report, or as artistic as that picture of the African large mammals, right? So, anything else? Yeah.
So most databases we see is, what's your opinion on like databases and virtual reality or augmented reality?
Yeah. So the question was, most of what we see is in 2D. What do I think of augmented reality and 3D? Well, I like how you phrased it that way, because now that that's become a reality, I'm starting to get that question. I think 3D on a 2D screen is generally a bad idea, because part of the way that we process that so effectively as with stereoscopic vision is, even with very subtle movements of our head, we can make more meaning of depth. And information doesn't get occluded as easily because we can see things. We get hints of what movement is. We're very good at noticing subtle changes as we move. So I think that we're going to start seeing some pretty promising examples of data viz that is in VR or AR in ways that we're just beginning to play with. I would love to say we have research scientists looking into that at Tableau, but we're just beginning to crack into that. I'm hoping we hire someone soon. Yeah.
Have you looked at different visualizations in different industries? I'm in the healthcare service and work with doctors. Is there a different way of representing the same data to them that more appeals to them than other industries? Have you looked at that?
So the question is, in different industries, are there better practices for data visualization? Is that, well, with apologies to anyone who's a doctor in the room, I find that the best way to show doctors information is to show them they're right. I used to work in health IT. No, I don't think so. I have not seen any firm, I think there are certain practices, time-based data works really well where you lay it out left to right. If increase or decrease is important, you want to use a line, those kinds of principles. I think there are probably patterns of use that will get used over and over again. In healthcare, there's a way that physicians or any care provider gets used to interpreting data about patients. And so if you were to randomly start moving things around that looked similar, that meant similar but meant different things. So I think I would worry more about how are you changing what they're looking at over time than saying I need to look somewhere else to find great examples. And then I think I can take maybe one or two more. Yeah.
Do you have any recommendations for further reading?
Recommendations for further reading, yes. Gosh, there are a couple books that I haven't read recently that I want to, but I know that Stephen Few's Show Me the Numbers is a pretty good one. If you want to read Tufte's books, they're pretty good as well. I would read either of Edward Tufte's first two books. I wouldn't read all four of them. I mean, if you like it, please do. I think to get into this, he gets into some great stuff in the first couple books and then gets a little bit more repetitive after that. The asterisk I would put on Tufte is he's too over-focused on simplifying what you draw. I think there's at least research that points that maybe oversimplifying can lead to less understanding sometimes too. So I haven't seen Cole Nussbaumer's book yet, but I really want to pick that up. I'm trying to remember, there's one more at the back of my brain, maybe I'll remember afterwards, but those are a couple of my favorites. And one more question, I thought I saw a hand over here. All right. Oh, yes, oh, so close, yeah. So you're asking about position, and I mentioned how the shelves are at the top of the screen, but in terms of position, yeah. I think that there's no better place to use position. I mean, I would use it liberally everywhere. I don't think I'm answering your question correctly, so maybe you could say it a different way. Ah. Mm. Well, so I think, so the question is, if I know there's some part of my data that's really important, where do I put it? And yes, at least in left to right language countries, we do tend to start on the top left and make sense from there. But there are other ways that visual attributes will also spring out as well. Color in particular, like the way that the red lines popped off the page. If you do have something that's really interesting about part of your data, you can use color to draw attention in a way that will probably pull away much more than position. Size as well. Labeling too, we didn't get much into that, but if with a thoughtful use of text labels, there's a reason why it's been forever in Tableau, you can pick a mark and say, show me the label for just this mark, because just that extra splash of shape of text, and you can format the text to call a little more attention there, is a great way to that complexity will draw the eye as well. So there are a number of ways to get attention, not just top left corner is a good way, but there are a number of ways to do it. So, well, thanks to everyone for your time and attention and staying. I appreciate it.